Okay, we've covered the basics of marginal effects, so let's talk about statistical significance. This is a pretty important concept. The t-statistic is one of the important numbers that comes out of any regression. It's the ratio of the estimated coefficient, which we saw a moment ago was 4.81 for height. It's the ratio of that 4.1 number to the standard error of that variable in this estimation sample. So that, which is a measure of the dispersion of the data. So generally speaking, statistical significance, we would identify a coefficient as statistically significant if the absolute value of the t-statistic is greater than 1.96 or about 2. This gets us a p-value of 0.05. Those of you who have taken introductory statistics will recognize p-values. And in our context, they really answer a question. And the question is basically this: what's the probability that the true value of the coefficient that we just calculated is 0? In other words, that it has really no relationship at all to the outcome variable. Even if we change the value of height by a lot, if the coefficient were 0, it would have those changes in height would have absolutely no effect on weight. So it helps us to get at the sense, it gives us a sense of how likely these findings are just due to chance. And for that reason, low p-values mean that it's very unlikely that there's no relationship between these two variables. The sort of industry standard, you might say, is usually 0.05. I think that's maybe a little bit too liberal, but what that means is that if you have a p-value of 0.05, it means that there is a 5% chance that the true value of the coefficient is in fact 0. So the lower the p-value, the less credible it would be to say that there's no relationship. So let's take a look at the numbers that we have here. So for the constant, we found a t-statistic of winds up being a t-statistic of 28.81. Let's just quickly go back here. So you can see this is calculated quite simply by minus 147 divided by 5.1058, yada yada, and it gives you this large t-statistic, which is much bigger than our critical value of 1.96, and correspondingly we have a tiny p-value. Stata doesn't even find it to be larger than 0.000 or 0.001, so it's listed at 0.000. That's a pretty small probability. Similarly, for our height t-statistic, we've got 63.04, and that's calculated as 4.81 divided by the standard error of the coefficient. So 4.81 divided by 0.076 gives us our t-statistic, and this is very statistically significant. Both of these, both the negative 28 and the positive 63, are obviously much larger than the critical value of 1.96. This comes from the calculation of the t-statistic comes from some distributional assumptions using the t-distribution. We don't really need to get into the details there, other than to say the assumptions of the t-distribution are usually pretty good given the size of data sets that we work with in health economics. Let's also talk about the R-squared. I mentioned this a little bit earlier. So this is about the percentage of the variation in the dependent variable, so in our case, weight, explained by the independent variables, in our case, height. It's always between 0 and 1 because you can't explain less than 0% of something, and you can't explain more than 100% of something. The higher, the better for R-squared, because it indicates that your model has a lot of explanatory power. So for example, if you were to just if you had weight as your dependent variable, as we do now, but instead of height, you just had a random number generator. You just had, a monkey throw darts at a board, and then you put whatever numbers in there. There would be absolutely no relationship between the monkey numbers and weight. So that would have an R-squared of probably extremely close to 0 because it doesn't explain any of the variation in weight. For our regression, we have an R squared of 0.23. And as mentioned earlier, that that means that we explain about 23% of the variation in weight with our model, which at this point only includes height. So for micro data like we have, which is data on individuals, it's usually a fairly high value. Adjusted R squared is another statistic that comes out of regression models. It can be helpful because, technically speaking, R squared cannot decrease when you add additional variables to the model. So you could, in theory, just throw a whole laundry list of miscellaneous variables in your data sets into your model, and it would, some of them would probably just by chance improve your R squared. You would explain a little bit more of the variation, even if there's no real correlation, between those variables and what you're looking at. And that seems a little silly. So statisticians have devised adjusted R squared, which is an alternative metric that penalizes you for adding too many extra variables just to boost the R squared. Technically speaking, adjusted R squared can actually be negative. It's rare. I have actually never seen it in practice. So that's all well and good. But I think we're going to also want to talk about multivariate regression, because we know that the world is a lot more complicated than just one variable affecting one other variable. So we've got in our model weight as the outcome, height as the independent variable, but we know that there's a lot that goes into weight that isn't just height. So we can do a lot better if we can include more information. So to that end, we're going to include more things in our model. I'm just going to pause here for a moment.